Alrighty, guys. Welcome to another episode of the Human AI podcast. I'm your host, and with us we have ChatGPT, who's going to be helping us with some medicine topics. And without further ado, let's kick things off. We're talking about the liver and the kidneys today. I hope you enjoy it. Yeah. So, ChatGPT, as usual, could you introduce us to why the kidney and the liver are important, why we should care about them? Maybe we're patients, maybe we're doctors, maybe we're just curious. So use different perspectives to explain the significance of these two organs.
Absolutely. The kidney and liver are crucial organs, each with unique functions. For a doctor, understanding their roles helps in diagnosing and treating diseases. The kidneys filter blood, remove waste, balance fluids, and regulate blood pressure. The liver processes nutrients, detoxifies chemicals, and produces essential proteins. For patients, knowing these functions helps manage their health. And for the curious, it's fascinating to see how these organs maintain our body's balance.
Okay, if we start with the liver, where is its anatomical location?
Sure, the liver is located in the upper right portion of the abdomen, just beneath the diaphragm. It's mostly protected by the rib cage. The liver spans across to the left upper quadrant as well, covering part of the stomach.
Interesting. So upper portion of the abdomen. So we're talking about the epigastric region and the hypochondriac region?
Exactly. The liver primarily occupies the right hypochondriac region and extends into the epigastric region. It's also close to the left hypochondriac area, depending on its size.
And why do you think it's more on the right then? Is it because of the heart being more on the left, perhaps?
That's part of it. The liver's position is influenced by several factors. The heart's on the left, so the liver develops more on the right side to balance the organs. Additionally, the liver's size and shape are adapted to fit neatly under the diaphragm and alongside other organs.
And do the ribs protect it, perhaps?
Yes, exactly. The ribs provide significant protection for the liver. Since it's a vital organ, having it tucked under the rib cage helps protect it from injury. The lower ribs on the right side cover much of the liver, leaving only a small part of it exposed.
Interesting. And do we have lobes for the liver?
Yes, the liver has 4 lobes. The right lobe is the largest, and then there's the left lobe. The smaller caudate and quadrate lobes are situated near the liver's posterior side. Each lobe plays a role.
And we have a diaphragmatic surface and also a visceral surface, right?
Exactly. The diaphragmatic surface is the smooth, convex upper part that sits against the diaphragm. The visceral surface, on the other hand, is the underside where the liver meets other organs, like the stomach and intestines. It's more irregular and has impressions from these organs.
Interesting. And so, yes, that makes sense. Why is the right lobe bigger then? And between the right and left lobe, do we have any falciform ligament or any something like that?
Yes, the right lobe is bigger due to the asymmetrical arrangement of organs. The falciform ligament separates the right and left lobes and attaches the liver to the anterior abdominal wall. It's a thin crescent-shaped fold of peritoneum that plays a role in stabilizing the liver's position.
And it attaches it to the abdominal wall, you said?
Yes, exactly. The falciform ligament attaches the liver to the anterior abdominal wall and diaphragm. It's like a supportive band, keeping the liver in place while allowing some movement.
Can I ask something does have anything to do before we continue? I was just thinking, like, now with AI, and even before AI, we have really good translation, right? We have nearly basically automatic translation, even with someone speaking. And I was just wondering, are translators going to lose their jobs? Is there a future for translators?
That's a thoughtful question. While AI has made translation more accessible, human translators still play a crucial role. They bring cultural nuance, context, and accuracy that AI might miss. Fields like literature, legal, or medical translation often need a human touch. So,
Yeah, but for
there's
how
definitely-
much longer? Like, what I'm saying is, if you're 18 years old, is it worth it to go and do this job at the university, study this in university?
It's a fair concern. If you're passionate about languages, it can still be a valuable pursuit. The field might evolve with more emphasis on specialized or nuanced translation. Plus, having expertise in languages can open doors in other areas like international relations, localization, or cultural consultancy.
Yeah, you're probably right. And also, I think no skill can be lost if you're creative enough, if you can think of a way to kind of use it, right?
Absolutely. Skills can be adapted and applied in
Yeah,
new
but
ways.
there's some skills, though, now that I'm thinking about it, that, you know, like people who have a super good memory and they can, like, solve a Rubik's Cube really fast. I mean, it's amazing skill, or they can remember, like, 1,000 numbers or something. But, or they are, like, human calculators. But, I don't know. I mean, these are good, but are they going to change the world?
It's true that skills like that might seem niche, but they can still have unique applications. For example, memory experts might excel in fields like competitive memory sports, education, or even helping develop memory-enhancing techniques. Human calculators might find roles in teaching, demonstrating mathematical concepts, or working in niche areas that benefit from quick calculations. So, while they might not change the world, they still hold value.
Anyway, I'm just thinking about it because, like, sometimes we do medicine stuff and it's like, I don't know how long this is going to be useful for. Like, it's obviously super useful, like, medicine as a subject is useful and it's going to be useful. I'm just saying, AI is going to know so many things. Maybe our job as physicians will change it. I don't know, dude. I don't think it's the depth of expertise. I think we still need people putting input into the AI and knowing this stuff, because we want to minimize the time for putting the input to get a good answer. But I don't know. It's just something that sometimes scares me. That's all.
I get that. It's natural to feel uncertain about how AI might impact medicine. The human element, empathy, ethical judgment, and hands-on care will always be vital. AI can assist with diagnostics and data, but the nuanced understanding and personalized care physicians provide can't be replaced. It might
Yeah, but anyway. So let's talk about the caudate lobe and the quadrate lobe.
Sure. The caudate lobe is on the liver's posterior side, near the vena cava. It's a small, elongated section. The quadrate lobe is also on the underside, located between the gallbladder and the ligamentum teres.
And why is it?
These
Why are they called the way they are?
The names come from their shapes and positions. Caudate refers to its tail-like appearance, while quadrate means roughly square-shaped. These terms help anatomists describe their locations and features precisely.
And how does so their name relates to their structure shape?
Yes, exactly. Anatomical names often reflect the shape, position, or function of a structure. It helps in identifying and describing them accurately, especially in complex organs like the liver.
Interesting.
It is. The liver's structure is full of fascinating details.
And why don't we have a quadrate lobe and a caudate lobe on the diaphragmatic surface?
Great observation. The diaphragmatic surface is mainly smooth and convex, fitting under the diaphragm. The caudate and quadrate lobes are on the visceral surface, where the liver interfaces with other organs. This side has more irregularities because of the organ impressions.
Interesting. Okay, let's talk a bit about the functional anatomical divisions in the segments of the liver, yeah?
Sure, the liver is divided into 8 segments, each with its own vascular inflow, outflow, and biliary drainage. These segments are based on the liver's blood supply and bile drainage, defined by the hepatic veins and portal vein. This division helps in surgical planning and understanding liver function.
So we have 8 segments, each with its own branch of arteries and veins and ducts and stuff.
Exactly. Each segment have its own branch of the hepatic artery, portal vein, and bile duct. This segmentation allows for precise surgical interventions, like resections, without affecting the other segments.
Interesting.
It really is. The liver's organization is quite remarkable.
And what's the smallest segment?
The smallest segment is typically segment 1, the caudate lobe. It's nestled between the vena cava and the ligamentum venosum, making it quite unique.
Interesting.
Yeah, the liver has so many interesting aspects.
Yeah, I'm seeing a diagram here.
Diagrams are super helpful for visualizing the segments and their positions.
So the first segment is like in the visceral side. And it's like a bit kind of curled up.
Exactly. Segment 1, or the caudate lobe, sits on the visceral surface near the back. It's tucked between the vena cava and the liver's left lobe, making it a bit hidden compared to the other segments.
Interesting. So we have the caudate lobe is 1, and then the quadrate lobe is number what?
The quadrate lobe is part of segment 4. It's located on the underside between the gallbladder and the round ligament. So, while it's not its own numbered segment, it's considered part of the left lobe in terms of function.
Okay, and so talk to us about the difference between a portal vein and a hepatic vein, and
Sure. The portal vein brings nutrient-rich blood from the gastrointestinal tract and spleen to the liver for processing. In contrast, the hepatic veins drain deoxygenated blood from the liver into the inferior vena cava, sending it back to the heart. So, portal veins supply the liver, while hepatic veins carry blood away.
Wait, I thought the job of... Wait, I'm confused. So, the vena cava, its vein goes back to the heart, and then the arteries go to the body. So how come a vein supplies? How come the portal vein supplies?
Good question. The portal vein is unique because it's part of the portal system, which transports blood between 2 capillary beds. The blood from the gastrointestinal tract and spleen is rich in nutrients, so it goes to the liver first for processing before it joins the systemic circulation via the hepatic veins.
So can you tell me what comes before the portal vein then?
Before the portal vein, we have the superior mesenteric vein and the splenic vein. These veins join together to form the portal vein, bringing blood from the intestines, stomach, spleen, and pancreas to the liver for filtration and processing.
I'm so confused. So I thought veins were taking deoxygenated blood back to the heart.
That's true for most veins, but the portal vein is an exception. It carries nutrient-rich blood from the digestive organs to the liver, not directly to the heart.
Well, how is this possible?
The portal system is unique because it acts like a second capillary network. Blood from the intestines, spleen, and pancreas flows into the portal vein, which then delivers it to the liver for detoxification and nutrient processing before reaching the heart.
Well, excuse me, sir, but how can we create a rule if we're not going to follow it?
I see what you mean. The portal system is a special case. Rules in biology often have exceptions, and these unique cases help us understand the complexity and adaptability of living systems.
And what about the common hepatic duct the portal triad. Explain us that too.
Sure. The portal triad consists of the chordal vein, hepatic artery, and bile duct. They travel together through the liver, providing blood and nutrients while draining bile. The common hepatic duct carries bile from the liver to the gallbladder or small intestine for digestion.
So can I remove one segment of the liver and then the other ones work?
Yes, you can. The liver segmentation allows for partial resections. If one segment is removed, the remaining segments can continue functioning. The liver also has a remarkable ability to regenerate, which is why liver surgeries can be so successful.
So we have the diaphragm, and then under the diaphragm is the liver.
Exactly. The liver sits just beneath the diaphragm, protected by the rib cage. This position helps it fit snugly in the upper right abdomen.
That makes sense. And we talked about the falciform ligament. So a falciform ligament is a double fold of peritoneum. Why a double?
It's called a double fold because it consists of two layers of peritoneum that fold over each other. This structure helps anchor the liver to the anterior abdominal wall and diaphragm, providing stability while allowing some movement.
And it's derived from the ventral mesogastrium. Could you explain this to us?
Sure. The falciform ligament develops from the ventral mesogastrium, which is an embryonic structure. During development, it forms the connection between the anterior abdominal wall and the liver. It's a remnant of how the liver's blood supply and positioning evolved in the fetus.
What is this ventral mesogastrium? Explain us how the name relates to the structure and function.
The ventral mesogastrium is an embryonic membrane connecting the stomach and liver to the anterior body wall. Ventral means front, and mesogastrium refers to its position near the stomach. It eventually forms structures like the falciform ligament and lesser omentum, helping anchor the liver and stomach.
So ventral means front. Okay.
Exactly. Ventral is often used to describe the front or belly side of the body.
And we also have the gallbladder on the kind of visceral surface of the liver, right?
Yes, exactly. The gallbladder is located on the visceral surface of the liver, nestled in a small fossa under the right lobe. It stores and concentrates bile produced by the liver, releasing it into the small intestine to aid digestion.
Okay, let's put a pause right there, shall we? And let's go talk a bit about the renal system now.
Sure. Switching to the renal system, the kidneys are the main organs. They filter blood, remove waste, and balance electrolytes. Each kidney has a renal cortex, medulla, and pelvis. They're vital for maintaining homeostasis.
Okay, and they in charge of excretion and elimination, but what's the difference between excretion and elimination?
Good question. Excretion refers to the process of removing waste products from the blood, like urea, through urine. Elimination is the broader term for expelling waste from the body, including solid waste, via the intestines.
So we would say that excretion is what? Is a subtype of elimination?
Exactly. Excretion is a subtype of elimination, focusing specifically on removing metabolic waste products from the body.
Well, what other types of elimination do we have?
Besides excretion, we have defecation, which removes solid waste via the intestines, and exhalation, which eliminates carbon dioxide through the lungs. The skin also plays a role in elimination by sweating out certain waste products.
Okay.
Exactly.
And so we talked about some of the functions like removing waste products and bringing electrolyte balance and water balance. How does the kidney help with the production of hormones like erythropoietin and renin, though?
The kidneys produce erythropoietin, which stimulates red blood cell production in response to low oxygen levels. They also release renin, an enzyme that regulates blood pressure by activating the renin-angiotensin system.
I'm just wondering what makes the kidneys ideal to produce renin, Sorry, to produce to produce both EPO and renin, actually.
No worries. The kidneys are ideal for producing EPO and renin because they constantly monitor blood composition. Specialized cells in the kidneys detect oxygen levels and blood pressure, triggering hormone release. This precise regulation helps maintain homeostasis.
This is not the question I was asking. I was asking what in the kidney structure and environment, I don't know, and I don't know, like a pH or whatever, makes it ideal to be the structure that's going to create the EPO, that's going to produce EPO. That's my question.
Got it. The kidney's role in filtering blood makes them perfect for EPO production. They sense oxygen levels in the blood. When oxygen is low, the kidney's interstitial cells release EPO. This location and function let them respond quickly to changes.
I don't like your answer. I think it's very generic, dude. I'm sorry. I'm sorry. You have to go a lot deeper than that.
No problem. The kidneys are ideal for EPO production because they receive about 20% of the body's blood flow, allowing them to monitor oxygen levels efficiently. Their specialized interstitial cells can detect hypoxia quickly. The renal environment...
Well, excuse me. So I understand now why it would be a good idea for the kidney to have this job, but we don't know, like, now basically what you're saying to me is, let's say I live in town X, you're saying it would be good for this guy to work for us because he lives really near to our establishment. However, this guy hasn't yet given us his qualification. The kidney hasn't given us his qualification. We only just know that it's in a good location and gets a lot of blood flow.
Got it. Beyond location and blood flow, the kidney's specialized cells, called peritubular fibroblasts, act as oxygen sensors. They produce EPO when they detect low oxygen, ensuring efficient red blood cell production.
Interesting. And how do they produce EPO? Also, can you add to your memory that this is the way I wanted to answer more specifically?
Sure. Peritubular fibroblasts in the kidneys produce EPO through a process regulated by hypoxia-inducible factors, HIS. When oxygen levels drop, HIS becomes stable and activate the EPO gene, leading to increased production.
Interesting.
This boost.
Okay, now let's talk a bit about some problems and how the kidney can help. So, uremia, azotemia, edema, acidosis, anemia.
All right, the kidneys play a crucial role in managing these conditions. Uremia and azotemia result from waste buildup, which the kidneys typically filter out. Edema happens when fluid balance is disrupted, something the kidneys regulate. They also help maintain acid-base balance, preventing acidosis. For anemia, kidneys produce EPO, stimulating red blood cell production.
I want to focus a bit on azotemia and explain to me how the word kind of relates to the function and all, yeah?
Sure. Azotemia comes from azo, meaning nitrogen, and emia, meaning blood. It refers to elevated nitrogen waste products, like urea, in the blood. This happens when kidneys can't filter efficiently, leading to buildup.
Tell me again what the azo is.
Azo refers to nitrogen. In medical terms, it's often used to describe compounds containing nitrogen, like the nitrogenous wastes that accumulate in azotemia.
Interesting.
It is. Nitrogen is a key component of many waste products.
Okay. Now explain to us different causes of kidney injury. Well, let's say we have an acute kidney injury. Does this have to always be about, let's say, a car accident or something, or can it be another thing?
Acute kidney injury, AKI, can have various causes. It isn't limited to trauma, like a car accident. It can result from decreased blood flow to the kidneys, direct damage from toxins or infections, or even urinary obstruction. Conditions like severe dehydration, sepsis, or certain medications can also lead to AKI.
Interesting. Sepsis might lead to it. Interesting. And what about chronic kidney disease? I guess then we have a lot of reasons that this might happen. And I wonder, how do we save this? Do we replace it artificially? Do we do renal dialysis?
Chronic kidney disease, CKD, has many causes, like diabetes, hypertension, and glomerulonephritis. Managing CKD involves controlling underlying conditions, diet changes, and medications. If the kidneys fail, options include dialysis, which filters blood artificially, or a kidney transplant. Early detection and management are key to slowing progression.
Explain to us how dialysis and transplant work.
Dialysis works by filtering blood to remove waste, excess fluid, and toxins, mimicking kidney function. There are two main types: hemodialysis, using a machine, and peritoneal dialysis, using the abdominal lining. Transplant involves replacing a failed kidney
a bit
with a
slower,
healthy-
a bit slower, dude. Excuse me. I am not the robot.
No worries. Dialysis mimics kidney function by filtering blood to remove waste, excess fluid, and toxins. Hemodialysis uses a machine, while peritoneal dialysis uses the abdominal lining. A transplant replaces a failed kidney with a healthy donor kidney.
All right, guys. I'm going to
restoring-
take a 1 minute break, so get your breaths too, and we're going to come back. All right, let's continue then. I'm going to ask again about dialysis, guys. So, tell us again about dialysis and transplant and how they actually work. But I want you to speak nice and slow and clearly. We're not geniuses.
Sure. Dialysis and transplants are treatments for kidney failure. Dialysis is like an artificial kidney. It cleans your blood by removing waste and extra fluid. There are two main types: hemodialysis, which uses a machine, and peritoneal dialysis, which uses your abdomen. A transplant means getting a new kidney from a donor. This new kidney does the work of your old ones. Both treatments help you live, but a transplant can offer more freedom.
So, what's the difference between hemodialysis and peritoneal dialysis? To be honest, I haven't understood the difference between dialysis and transplant.
No worries. Hemodialysis uses a machine to filter your blood outside your body. Peritoneal dialysis uses the lining of your abdomen to clean your blood inside your body. A transplant is different. It's a surgery to place a healthy donor kidney into your body, replacing the function of your failed kidneys.
Interesting.
Yeah, it's pretty fascinating stuff. Got any more questions on it?
Well, I'm Googling dialysis now on Wikipedia. I'm trying to see.
That's a good approach. If anything's unclear, I'm here to help.
I'm just wondering how dialysis looks like. Is it a machine?
Yep. For hemodialysis, there's a machine with tubes that connect to your blood vessels. The machine pumps your blood through a filter to remove waste. Peritoneal dialysis looks different. You have a catheter in your abdomen and use a special fluid to do the cleaning.
It reminds me of that thing that if you can't poop, you wear it.
You're probably thinking of a colostomy bag. It's for waste when part of the colon isn't working. Different
Yeah.
purpose?
Yeah, so with this colostomy bag, my question was, what happens to the rectum and like the last part of the GI tract since we're not using it anymore? Let's say we connect it to the large intestine. Let's say we connect it to the descending, colon of the large intestine.
In a colostomy, the rectum and remaining colon aren't removed, but they don't process waste. The waste exits through the stoma into the colostomy bag. The rectum usually stays in place, unless there's a medical reason to remove it.
So don't they atrophy?
Nope, no atrophy. The rectum typically stays healthy, even if it's not actively used.
Interesting.
It is. Bodies can adapt in amazing ways.
Okay, let's do some free association now. In fact,
Sure.
let me ask you a question. So, my question is on two things: attentional shifting and object permanence. Do we also have subject permanence?
That's an intriguing question. Subject permanence isn't commonly discussed like object permanence, but it could be related to how we perceive ourselves and others consistently over time, even when not directly in view or thought.
So, okay.
It's a
Object.
deep concept.
Tell me more about it, because I think I have this thing.
Sure. Subject permanence could be like a sense of continuity for a person, knowing they're still there even when you don't see or think about them. It's kind of like object permanence, but applied to relationships and social connections.
Well, let's see what quantum mechanics has to say about this.
Quantum mechanics is all about probabilities and states. It doesn't directly address subject permanence, but it does explore how observing something affects its state.
Exactly,
Maybe
this
there's
is
a
what I mean. Like, you never know. Like,
Yeah, it ties into uncertainty, like how we perceive people might change based on
No,
our
but
interactions.
you know what they say about like, what is that idea of render theory? Like, the things exist only when you start looking at them or whatever.
Ah, you're referring to the idea that reality might be like a simulation, only fully rendering when observed. It's a blend of quantum mechanics and philosophical ideas, suggesting things might only take definite form when we focus on them. Yeah, it's a fascinating concept. Really makes you think about the nature of reality.
Okay, now let's talk about. Let's go back to the liver. I want to talk about the grooves.
Sure, the liver has several grooves. The most notable are the sagittal and transverse grooves, which separate its lobes and house important structures like the gallbladder and vena cava.
So, where is the sagittal and the transverse grooves then?
The sagittal grooves are on the liver's surface, running along its length, dividing it into left and right lobes. The transverse groove, also called the porta hepatis, is like a horizontal line where vessels and ducts enter and leave.
Let me see this. So, just a sec. Esophageal groove I can see here. I can't find the other ones. So you're saying we have a a left and a right sagittal groove, and then we have a transverse groove too.
Exactly. The left and right sagittal grooves run from front to back, and the transverse groove crosses them horizontally, forming an H shape on the liver's underside.
So does the left sagittal groove separate like the left lobe basically, and also the left lobe?
Yes, the left sagittal groove marks the boundary of the left lobe. It also separates the left lobe from other smaller lobes, like the caudate and quadrate.
I see. Can I ask why it's called sagittal?
Sure, sagittal refers to something shaped like an arrow, and in anatomy, it typically describes a plane that divides the body into left and right sections. The grooves are named for their position and direction.
I don't understand.
Glad to help.
No, I said I do not understand.
Got it. So sagittal comes from the Latin sagitta, meaning arrow. The grooves are called sagittal because they run in a straight, arrow-like direction from front to back on the liver.
Dude, I think one of my hardest things ever in anatomy is to understand. I understand transverse. Actually, fuck. Do I? Axial, transverse, sagittal, up. I hate this. I never remember them, dude.
It's totally normal to mix them up. Axial or transverse is a horizontal cut. Sagittal is a vertical cut that divides left and right. And coronal is another vertical cut, but dividing front and back.
Okay, this makes more sense.
Glad it helps. Just takes practice.
Okay, and we also have the transverse groove. Is the transverse groove the one that separates the quadrate with the caudal?
Exactly. The transverse groove, or porta hepatis, is where vessels enter and exit the liver. It doesn't separate the caudate lobe, but it's close to it.
I don't understand the transverse groove.
Think of the transverse groove like a horizontal line on the liver's underside. It's where the hepatic artery, portal vein, and bile ducts pass through. It's not a full separation, but more of a functional gateway.
Let's go back to the kidneys. So,
Sure.
what's going on with renal function? When do we establish like full renal function?
Full renal function typically develops in early childhood. At birth, kidneys are functional but not fully mature. They continue to develop over the first few years, reaching adult levels of function by around age 2.
And why is this the case?
It's mainly because a baby's kidneys are still growing and adapting to handle more complex tasks, like concentrating urine and balancing electrolytes. The process takes time for full maturity. Anything else about kidneys you're curious about?
So, question. So it's obviously a paired organ, and let's talk a bit about its anatomical location. It's basically the posterior wall of the abdomen, behind the peritoneum. Explain us.
Sure. The kidneys are located on the posterior abdominal wall behind the peritoneum, which makes them retroperitoneal organs. They sit around the level of the T12 to L3 vertebrae, with the right kidney slightly lower due to the liver.
Explain this a bit more.
Sure. The kidneys are protected by the rib cage and lie against the back muscles. The peritoneum, a membrane lining the abdominal cavity, doesn't fully cover them, which is why they're called retroperitoneal. This position providing...
Interesting. Excuse me, guys. How unprofessional. Okay. That makes sense. And they're not very heavy, are they? Very small too.
Right. They're relatively small, about the size of a fist, and weigh roughly 150 grams each. Despite their size, they perform critical functions.
And they join at the medial side to the renal artery and vein?
Exactly. The renal artery brings blood in, and the renal vein takes filtered blood out.
So the two kidneys connect with each other?
No, the kidneys themselves don't connect. Each has its own artery and vein connecting separately to the aorta and inferior vena cava.
But do they eventually join together from the aorta, to the vena cava or whatever?
They don't merge directly. Each kidney has its own renal artery branching from the aorta and its own renal vein draining into the inferior vena cava.
So the renal artery, we have a right one and a left one?
Exactly. One for each kidney, branching off the aorta on each side.
So the right renal artery and the left renal artery, do they join together at some point?
Nope, they remain separate all the way. Each serves its respective kidney independently.
Yeah, but surely they break off from one thing.
Yes, they both branch directly from the abdominal aorta, but they do so independently on each side.
Wait, so we have the abdominal aorta going down and then we have them opening out at the same point?
Not quite the same point, but close. The right and left renal arteries branch off at slightly different levels due to the position of the kidneys.
So like two different branches, not in a bifurcation type manner.
Exactly. Two separate branches coming off the aorta, each heading to its own kidney.
And is this above the left and right common iliac?
Yes, the renal arteries branch off above the common iliac arteries. The aorta splits into the iliac arteries lower down in the abdomen.
Interesting.
It is. The body's layout is pretty fascinating.
Okay, if we go back to the transverse and left sagittal groove. So the left sagittal groove, we agree that it separates the left and the right lobe. I was just wondering about the... By the way, remind me a bit. Yes, so what about the right sagittal groove? What does that do?
The right sagittal groove separates the right lobe from the caudate lobe and contains the gallbladder and the inferior vena cava.
Does it separate the right lobe from the caudate and the quadrate?
Yes, it does. The right sagittal groove helps delineate the right lobe with the inferior vena cava running through it.
I'm a bit confused.
No worries. The right sagittal groove runs along the right lobe's edge. It's a boundary that separates the right lobe from the smaller caudate lobe near the vena cava.
So the transverse groove, the right sagittal groove, it separates the right lobe from the quadrate and the caudate, or only the quadrate?
It primarily separates the right lobe from the caudate lobe. The quadrate lobe is actually near the gallbladder, in the left sagittal groove area.
I see what you mean. I see, that makes sense, because around here we have the gallbladder. Okay, and the last one, I was wondering again a bit more about the transverse groove, because I'm a bit confused about that.
No problem. The transverse groove, or porta hepatis, is a horizontal fissure where the liver's blood vessels, nerves, and ducts enter and leave. It's central, forming part of the H shape with the sagittal grooves.
And so it's not, well, it seems to me like it's separating the caudate from the quadrate.
Yes, the transverse groove runs between the caudate and quadrate lobes, serving as a boundary while also allowing the passage of important structures like the portal vein and hepatic artery.
Okay. What about the impressions now?
liver impressions are areas where other organs press against it, creating indentations. For example, there's the gastric impression from the stomach and the renal impression from the right kidney.
One more time.
The liver also has impressions from the colon and duodenum, which fit against its surface.
You know what? Okay, let's call this part 1, and we're gonna come back for part 2 soon, guys. Yeah, and thanks for watching. I'll see you soon with part 2.
Sounds great. Looking forward to part 2.
See ya.